For number 11, we're going to find the p-value, and it is a left-tailed hypothesis test, and we have a specified test statistic z-value here. This is discussed in chapter 7.2. Visually, what we're trying to do is find the probability of being further into the left tail than a specific z-value. The probability of being at a specific critical value or even further into the left-hand tail of the distribution. In Excel, we can use the formula equals norm.s.distribution here, put in the z-value, comma true, and when you hit enter on that, it will give you the probability of being at that z-value, that critical value, or even further to the left of it, and here it is. With every hypothesis test, we compare the p-value, the probability value, to our significance level alpha, and if it is less than alpha, we will reject the null hypothesis. In this case, since our alpha is 0.10, our p-value is less than that, so we will reject the null hypothesis. 12 is similar to number 11. We have a right tail test, and our test statistic z-value here is 1.38. We're going to look for the p-value of that. We're in 7.2, a right tail test. We're looking for the probability of being at a specific critical value or even further into the right-hand tail of the distribution. In Excel, we can use the formula equals norm.s.dist distribution and put in our critical value, and that gives the probability of being at that critical value or further to the left. And so if we want to find the probability of being further to the right-hand tail, we would do 1 minus that answer. And that gives the probability then of being from that critical value further to the right-hand tail of the distribution. For the second half of the problem, we have to decide whether to reject our null or fail to reject it. And this is all based off of our significance level. We compare the p-value to the significance level. If it was less than our significance level, we would reject. 0.08 is not less than 0.05, so we fail to reject our null hypothesis. For number 13, we're dealing with the situation here in chapter 7.2 where we actually know the population standard deviation. Here's the formula we're going to need to use to find the test statistic z. And here we're doing it in Excel. We have the sample mean minus our null hypothesis, and you divide all that by the population standard deviation divided by the square root of the sample size. And that gives us our test statistic z. To find the p-value of that test statistic, norm.s.distribution, and enter in that value, comma true, and that gives the probability of being at that value or less than it. So if you want to know the greater than probability, you need to do 1 minus the less than probability to get your result. In this particular example here, a state school administrator is declaring that the mean is more than a certain value. So that claim is going to be our alternative hypothesis, the more than, and the complement of that, less than or equal to, would be our null hypothesis. And since we are doing a more than a right-hand tail test, what we just looked at here in Excel, we need to do the 1 minus the left-hand tail probability to get the p-value of being more than a certain critical value. The conclusion of a hypothesis test, we always compare the p-value to our significance level. If it was less than the significance level, we would reject the null hypothesis. This value is more than our significance level, so we fail to reject the null hypothesis. So at our significance level, which was stated here, we're failing to reject, so that means there's not enough evidence to support the alternative, which was our claim here, that in this case, the grades are more than 275. And number 14, we have someone claiming that the mean tuna consumption by a person is 3.1 pounds per year, and that's what we're going to try to challenge here with a hypothesis test. So our null hypothesis is that 3.1 actually is the mean. Our alternative will be that the mean is anything but 3.1 pounds per year. We have information about a sample of 50 people. We have the mean from that sample and the population standard deviation. So what we want to do is calculate the p-value for that sample. So in 7.2, if we come down here, this is a situation where we know the population standard deviation. So this is how we'll calculate the critical z-value. So doing that calculation here, we take our sample mean minus our null hypothesis for the mean. And on the bottom, we take the population standard deviation and divide by the square root of our sample size. Doing that is going to give us our standardized test statistic here. And we're going to use that to calculate the p-value. Now, our alternative hypothesis was not equals to, which means this is a two-tailed test. So our critical value, we can use Excel formulas to find the probability of being at that value or further into the left-hand tail. And then by symmetry, we just double that to also get the probability of being at the symmetric value or further into the right-hand tail. So here is our critical value in Excel, norm.s.distribution. That critical value, true, the probability of being there or even further into the left-hand tail. And we take that value and multiply it by 2, and we get a result for the probability of being either in the left-hand or the right-hand tail from that critical value. To conclude our hypothesis test, we always compare the p-value to our alpha, and since this is larger than alpha, we fail to reject our null hypothesis. For number 15, our situation is that a fast food restaurant are making a claim that the mean sodium content in their breakfast sandwich is no more than a certain number of milligrams. So their claim is that it's at that value or less than it. So there is an equal statement in there. That is our null hypothesis, at the value or less than it. Our alternative would be the complement greater than that specified value. In 7.2, this is a situation where we know the population standard deviation. So we're going to use this formula here to find the standardized test statistic and our p-value. So in Excel, we take our sample mean minus our null hypothesis for the mean. That is the top part of the fraction. And on bottom, we have the population standard deviation divided by the square root of the sample size. And doing that calculation, it gives us our standardized test statistic. That's actually part C here. What we compare that test statistic to is our critical value. And the critical value here in part B is completely based upon our significance level, which in this example is 0.10. To find the critical value that would be associated with 0.10 or 10% equals norm.s.inv. and you get that critical value associated with the 10%. Now, in this particular example, our alternative hypothesis is a greater than. Further to the right in the tail, we have a right tail test here. And so Excel is always giving us a left-hand tail value for our critical value. By symmetry, the right-hand tail value would be the same numbers, just the positive for our critical value. And so a greater than alternative, our rejection region is greater than that critical value. In this particular example, the test statistic is not greater than our critical value. In fact, it's a negative number, so it is quite a bit below our critical value. And so we fail to reject our null hypothesis.